So our next speaker is Przemek Dera from the University of Hawaii, who will give us a synopsis of the PX2 program at GSECARS for extreme Xtallography. So Przemek, will you please share your screen and unmute yourself?
So yes, good morning and thank you for the invitation. It's really nice to see so many participants in this workshop. I guess my job for today is to talk about the project that we have been pursuing at GSECARS with the support of Compress funding since about 2015. The project is called Partnership for Extreme Crystallography, and its goal was to equip one of the bending magnet beamline experimental stations at GSECARS with tools suitable for studying structural problems that happen at high pressure, structural phenomena. The project involves quite a lot of personnel. We have two Compress funded beamline scientists, Dongjiao Zhang and Jingui Zhu. I'm the person who helps remotely, usually from Hawaii, and I deal with the administrative issues and with software sometimes. At GSECARS, we have a lot of help from Mark Rivers, Peter Eng, Joan Stabs, and Vitaly Prokopenko, and I'm very grateful for all the time and all the thoughts that they contribute to this project. The project is located at the beamline 13 BMC. This is a side station on the bending magnet beamline at GSECARS. The diamond anvil cell program, the PX2, receives currently about 75% of beam time available for the bending magnet. We have two beamline, available for the BMC. We have two beamline scientists funded by Compress. The motivation for developing this program has stemmed from the need for understanding the structural transformations that minerals and rocks undergo under high pressure and high temperature. So if you think about Earth as a very complex and dynamic system, we have these major geologic events that significantly affect our existence as humans on the surface. We as humans also significantly affect the ecosystem and Earth as a whole. We explore minerals and resources, and the gases that our activity emits affect, atmosphere and so on. So understanding the structure, composition, and properties of the Earth interior offers us a better chance to live in harmony with our planet and understand things like geohazards and mineral resources and so on. I'm a crystallographer by training, and for me, there's a very close link between physical and chemical phenomena that happen to individual minerals inside the Earth interior and large-scale geological processes. So studying phenomena such as elastic deformation or plastic deformation, structural transitions, magnetic transitions, melting, and so on, is directly connected with these large-scale phenomena like earthquakes, plate tectonics, volcanism, and so on. I like this illustration that shows an interplay between an experimental diffraction pattern at the bottom and the mountain range formation at the top. That's what we are trying to achieve by performing these high-pressure experiments with minerals. The mission that we set for the project was to try to take the best possible advantage of the existing bending magnet source. It's obviously not as intense as the insertion devices, but if you use it smartly, you can still provide advanced crystallographic tools that would be specifically designed and optimized for the type of experiments that you want to conduct, and take the best possible use of all the photons that you have. Besides providing these advanced capabilities for structural characterization, mainly by means of single crystal and multi-grain diffraction, we also wanted to focus on developing methods for performing these experiments in laser heated diamond anvil cell with single crystal samples. And I will talk about specific challenges for this type of experiments in a moment. We also wanted to keep our eyes open and explore new methods and devices for straight-driven structural transformations and chemical reaction monitoring in situ besides diamond anvil cells. In terms of instrumentation layout in our experimental station, this is a somewhat unusual instrument, different than most other high-pressure experimental stations at synchrotrons. The instrument is built around a 6-circle heavy-duty Newport diffractometer. So this is a device that allows us to reorient the sample with respect to the beam and reorient the detector or a set of detectors around the sample. You can see this really large instrument at the center. This is a heavy-duty instrument that allows us to carry a sample as heavy as 25 pounds, I think, with preserving the sphere of confusion, with preserving the positioning of the sample to less than 20 microns or so. The station uses a monochromatic beam, which is available at 28.6 kiloelectronvolts, which is very nice. Just to remind you, in diamond anvil cell experiments, we deal with the effect of absorption of X-rays by the anvil. So working with X-rays below 20 kiloelectronvolts creates a problem with significant absorption effect. So this is a very comfortable range of energy for this kind of experiments. Working at higher energies also allows us to fit more peaks in terms of their 2 theta angles into the cone of the diamond anvil. So we have access to more observations. The beam is focused to a size of about 12 by 18 micrometers. And we have a range of detectors. Most recent addition is a Pilatus 1M detector, which was co-funded by GSECARS and Compress. The design of this instrument from the very beginning tried to emphasize this desired capability of being able to hit crystals, single crystals inside diamond anvil cells at high pressure. So the challenge with this is that during a single crystal data collection, we have to rotate the sample with respect to the beam rather than keeping it still, as is the case for powder diffraction. So this means that both the X-ray beam has to hit the sample and the laser beam has to provide a constant illumination and more or less constant temperature as the sample rotates. So for this reason, the instrument has a special optical platform that is able to rotate with the sample by means of one of the 6 circles of the diffractometer. These are some close-ups of the specific setup. So the sample has 4 different rotation axes available to reorient the sample. And then there are 2 additional circles that allow us to rotate the detector. This is the, I'm sorry, let me switch my pointer to the laser pointer. This here is the optical platform with a long distance lens that allows us to look at the sample while the sample is rotating. We don't have to retract the optics as is usually required for many other instruments for diamond anvil cells. Obviously, to make these experiments convenient and reliable, we provide a range of auxiliary devices that help to automate the experiment, particularly useful during the times of pandemic where a lot of users have to ship their samples and we have to set them up for remote experiments. So the instrument has membrane controllers available. We have 2 of them, so it can work either in a simple setup where you have just a pusher membrane or in a setup with 2 membranes with a pusher and the second membrane that pulls the cell apart. We have temperature controllers and heaters available for resistive heating. And I showed some of the optics that allows to perform these laser heating experiments. Since 2015, we've developed a pretty nice user base that comes from all around the world. We have many users in the United States. You can see me sitting here on this piece of rock on the left side in Hawaii. We have a nice group of users from Europe as well as from Asia. So it's growing and pretty active. Again, since 2015, we have grown this program and made the instrument reliable and pretty easy to use. So we see an increase, a steady increase in requests for beam time and increasing number of experiments. This was obviously affected by the pandemics and by some of the changes in APS regulations regarding access of users from certain countries, but we still maintain a fairly heavy demand for beam time, and you can see the oversubscription rate. It's not quite as high as what Quentin was showing, but this is because the source in our experimental station is bending magnet, so it's much lower intensity. It's very difficult to perform multi-megabar experiments with bending magnet beam. You can see the publication output on this figure on the right side. So we started in 2015 with the first experimental user beam times, and then we have now reached a level where our users are producing about 30 papers a year out of this 75% of beam time. So it's pretty healthy and growing. From early on, we had to invest in developing software solutions for our users, because our experimental station needed to emphasize these a little bit more advanced and esoteric experimental approaches and methodologies. There wasn't at that time very good software available that would be commercial and could just be handed to users. So we started by writing our own code called GSECARS that was used quite extensively until recently by most of users performing single crystal experiments. You can see here from Google Scholar that by today, the software use has been cited by almost 140 papers. Today, we offer it as one of the options, and the other options are the commercial packages developed by companies that make diffractometers, Bruker and Rigaku, which nicely implemented features allowing to work with synchrotron data just as easily as you can with data coming out from a home diffractometer. So for people who have access to X-ray diffraction facilities at their universities, this provides a nice way, because they can have their students be trained at the home facility with the use of this software when beam time restrictions are not a problem, and you can learn at your own pace, and then you can come to the synchrotron knowing how to use this software and process your data quickly and efficiently. Our users bring a variety of projects. Most of them involve some kind of structural transformations, sometimes chemical reactions. We have a lot of users studying transformations in inorganic and sometimes organometallic solids. We have an example of a study like this here, where a pressure-induced ferroelectric transition was studied in one of the anti-perovskites. Just like I said at the beginning, because the source of X-rays for our experimental station is a bending magnet, it creates a little bit of a challenge with the number of photons available for diffraction. So samples in diamond anvil cells are very small. Some of them don't scatter X-rays very strongly. So producing a sufficient signal to noise is a little bit challenging. So this translates to a difficulty with producing super high profile papers in journals like Nature or JACS. But because of the design of this instrument, and because of the high quality of detector and focusing and so on, we are able to often offer these opportunities that enable people to still discover these exciting phenomena and report them in high profile papers. This is another example of a project that was driven by a user's desire to develop a new way of performing experiments. Just like Quentin emphasized in his talk, we always listen to users if they bring interesting scientific projects and are willing to adapt our instrumentation to their needs. This was a project where we developed new solutions for studying solid inclusions in diamonds. You can see a picture of diamond here. This is performed in collaboration with the group of Steve Jacobson at the Northwestern University. So to make this possible, we developed a combination of experimental tools that allow to perform radiography and to some extent the tomography, allowing to locate the grain by an absorption contrast and then collect X-ray diffraction data from that location. In terms of minerals that form rocks in the Earth interior, despite the fact that our source is only a bending magnet, our users have been able to perform successful experiments that basically span all of the layers of the Earth. These are some examples on materials that are relevant for understanding the Earth core. Some of the iron compounds and alloys formed with light elements that are expected to be present in the Earth interior. So the advantage of using our instrument is that because it emphasizes and specializes in single crystal experiments, as long as a sample of this prototype Earth core material can be made available in the form of a single crystal to start with, we can detect very minute, very subtle transformations, sometimes magnetic transitions, changes in magnetic ordering, sometimes small changes in symmetry of these phases, and link them into geophysical observations coming from seismic measurements. Most of our users, however, specialized in experiments involving phases present in the Earth mantle. This narrows the pressure range to a little bit more manageable with the X-ray flux that we have available. These are some examples of work done on minerals from the pyroxene family, and here on a calcium oxide of new type that was synthesized in laser heating experiments. So the motivation for performing these structural studies of minerals that are present in Earth mantle from one of the possible motivations is to understand the processes that happen in subduction zones. Subduction zones are these interesting boundaries between tectonic plates where stuff happens, where properties, thermal properties and pressure conditions are a little bit different than in the average mantle, where we have transport of material from the surface to the deep Earth. So seismologists tell us that subduction zones located in different places around the world have different thermal profiles, and they have different geometries. Some of these subduction zones level off when they reach the transition zone of the mantle. Some of them are able to penetrate to the lower mantle, and being able to understand these subtle transformations in minerals that are present in large quantities in subduction zones may allow us to explain how subduction works better. So my personal interest in this as a solid state chemist and crystallographer was to understand how transformations of different coordination states of the main elements that are present in these phases change as a function of pressure and temperature. And my hobby has been to look for unusual states. So we know that silicon, which is the building block of most rock forming minerals, at conditions of low pressure and at ambient conditions prefers a coordination number of 4 and forms these nice tetrahedra that like holding hands and forming chains and layers and so on. However, when you pressurize these minerals, they transform to a higher coordination number to accommodate higher density. So in high pressure phases of silicates, we often find octahedral coordination and coordination number of 6. I'm showing here a figure from, I think this was from Dan Frost's paper, that shows the major phases of minerals present at different depths within the mantle. You can see that the upper mantle is dominated by 4 coordinated phases, and then in the lower mantle we have perovskites, which are 6 coordinated. Some years ago, almost 10 years ago now, we set out on this quest of exploring high pressure behavior of this silicate family of pyroxenes that has a 4 coordination number at low pressure and is present in large quantities in Earth mantle and subduction zone. Some of the first experiments were done in collaboration with Jay Bass and John Parisi. We found, looking at single crystal diffraction pattern, some interesting transformations that happen at fairly low, surprisingly low pressures, only about 13 gigapascals in this first study of ortho-enstatite. With the use of these software tools that we developed for the beamline, we were able to explain structurally what it means, how bonds and atoms transform during these transformations, what it means for density, what it means for physical properties. We found that the starting material that has 4-coordinated silicon at about 13 gigapascals transforms first through just a rotation of tetrahedra and change of kinking angle, then through a change of coordination number and formation of these sites where an effective coordination number of silicon becomes 5, and then finally at higher pressure formation of a 6-coordinated sites, all through subtle displacive phase transformations that come with fairly small changes in density. So things like this are really difficult to detect and explain if you only have powder diffraction at your disposal. But with this single crystal diffraction method, because it's so sensitive to detecting minute structural changes, it's possible to explain how this all works. We looked now over these last 10 years at the whole range of different pyroxenes, and we found a number of these transformations that happen both at ambient temperature and at higher temperatures. This is an example of diopside where structural transformation similar in nature to the one that we found in enstatite happens at a much higher pressure at about 60 gigapascals and also leads to phases with 5 and 6 coordination number. My fellow scientists at APS, Jingui Zhu and Dongzhou Zhang, came up with this new diagram of layering of the subduction zone, which incorporates information about these metastable, reversible phase changes that we found in our experiment. This still needs to be tested whether there's any evidence of this in seismic data, and has to be tested in geophysical modeling of the subduction process as well. But we have some general trends that we discovered that apply to orthopyroxene, sodium poor clinopyroxenes, and calcium rich pyroxenes. Recently, we started collaborating with a group at Warsaw University in Poznań, led by Professor Krzysztof Woźniak, which specializes in Hirschfeld atom refinement. So this is another technique for structural analysis, which basically gives you the ability to model electron density rather than just atomic positions. So when you want to look at unusual coordination states of mineral phases, this allows you to directly see whether a bond exists between two atoms. It allows you to see electron density that might be responsible for electrical conductivity, thermal conductivity, and so on. It's still a work in progress, but it's very, very promising and seems to be really a major step forward in our ability to see these fine details of rearrangements that happen as a function of pressure. One of our major goals was to try to develop this method allowing to heat crystals at high pressure to temperatures of several thousand degrees with a laser, while we can still rotate the sample in the diamond anvils and collect the data. So this is some of our work done by Dongzhou Zhang and Jingui Zhu. First, with just crystals in air, you can see here a crystal of iron oxide that was heated to almost 1,500 degrees. The most recent version of this experiment uses the concept that was introduced by Leonid Dubrovinsky in this paper in 2017, where diamonds with regular shape are replaced with diamonds that have spherical tables that allows to keep the length of the path of light, laser light through the anvil more or less constant, and dramatically improves our ability to uniformly and heat at constant temperature. These are some examples from recent experiments we performed with these new types of anvils on a garnet crystal. So you can read the temperature very stably over the data collection time. You can perform structural determination, determining how bonds respond, how volume responds to these changes in pressure.
1 minute.
Thank you. I'm going to skip this part. We are working on a project to implement a new type of high pressure device, a high energy mill into the beamline to allow us to look at impact phenomena and chemical and physical transformations of minerals and inorganic materials. But I don't think I have time to go through this in any detail. So I would just like to wrap up by thanking for your attention and giving you the summary. So PX2 is now a mature facility with well-established user base and sustainable publication output. Despite being located at a lower brightness bending magnet beamline, it takes excellent advantage of techniques and solutions that can best benefit from the available beam characteristics. It offers unique instrumentation and set of techniques to the mineral physics and material science communities. We adapted well to remote operation. We have many users who send samples and perform remote experiments. We invest in user-driven new technique development, and we greatly benefit from collaboration with the staff of GSECARS as well as users from universities. So if you are interested in collaborating and performing experiments at our facility at GSECARS, you are certainly welcome to contact us. Thank you very much.
Thank you, Przemek, for this very comprehensive overview of the PX2 project and these model examples of what users can do at the beamline. If you have any questions, please raise your hand now or type them in the chat. We have a question from Vitaly. Please unmute yourself.
Hey, Przemek, thanks for your talk. You didn't mention anything about the APS upgrade. What is your vision? Can you elaborate a little bit on it?
Yes, thank you for the question. I think the extent of benefit for our specific instrument is going to be a little bit less pronounced than for the insertion devices, but obviously for every high pressure experiment, being able to focus the beam to a smaller size and having more photons is very advantageous. So I think with this lower emissivity of the APS after the upgrade, we will have a benefit of both. I don't think it will dramatically change the way we perform experiments or open doors for completely new types of experiments we can perform at BMC, but I think it will improve the quality of data you can get, and we will also extend the range of pressures and temperatures and how small samples you can measure.
So basically, you say that probably in situ laser heating experiment collecting single crystal data will benefit significantly after APSU.
Oh, most definitely. Yeah, that's probably the most significant.
Okay, thanks.
That's great. We have a question from Claire. If you could unmute yourself.
Hi, thank you. I think that you might have already begun to touch on it with Vitaly's question, but I was curious about the beam size and the flux during with recrystallizing samples at high temperatures. So if that's something that'll benefit from the upgrade, if you could elaborate more.
Yes, so that's one of the bigger challenges. When you start heating samples, there's always a thermal gradient. When the samples go through a transition, different fragments of a crystal might go through a transition at different times, so it leads to a crystal breaking up into pieces. So when you perform these high temperature experiments that go across a phase transition, you usually end up with multi-grain samples. Our goals for analysis of multi-grain samples are a little bit different than what Quentin was discussing. So we would be interested in merging data, indexing data that come from these differently oriented grains, and merging them together to increase coverage and redundancy of structural information, and to provide unambiguous indexing of the high pressure phase if you don't know what the structural arrangement is. So in cases like this, the size of the beam determines how many grains contribute to your diffraction signal. From our experience in these first heating experiments, most of these small fragments are about a micron size. So if you are constrained to a beam size like we have right now, about 12 by 18 microns, you're working with maybe 20 or 30 crystals at the same time. So this is convenient because you have a lot of crystals that have different orientations and contribute unique pieces of information, but it's a challenge if you have to analyze the data at the time of performing the experiment. It's a great challenge. So if we can reduce the beam size to say 5 microns, it's going to dramatically decrease the complexity of the analysis. This is what is now the case at insertion device experimental stations, and in every case when we produce these multi-grain samples, performing the experiment at Vitaly's insertion device beamline is much easier in terms of interpretation, because you have signal only from maybe 5 crystallites rather than from 50.
Thank you, Przemek.